and it hits, and I set it back, so it draws the rest. This is done extensively in games. Like here, we switch between text mode and actually that graphic is text mode as well. It's tile-based mode, and I need two raster interrupts to do this screen splitting. Another example here is this uses at least 3 raster interrupts to do the 3 parts of the screen which scroll differently. And the demo we saw uses screen splitting a lot as well. But what's also interesting about this demo is it uses the area outside of the screen area in the border. So first there's the raster bars, which are pretty easy to do because all you have to do is change the background color and change the border color at the same time, then delay a few cycles until you're in the next line and repeat the whole thing. And there's extra graphics down there. That is a little bit more tricky. I'll show you that trick now. You remember that we can switch the screen between 24 line mode and 25 line mode, so this is 24. If we look at the bottom left of the screen, this is 25 lines, this is 24 lines. Now what we do is we set the screen to 25 lines, which would be here, and set an interrupt handler or set a raster interrupt at that red dot. So we let it paint the whole screen up to the red dot. Now we change the line where the vertical border would start up to this address. And now that trigger, when it has to turn on the vertical border, never triggers, so it just continues painting the screen. It does not paint any more characters because it's not programmed to do that, but it can paint sprites there. So while normally if you had sprites, that would be behind the border. If you use that trick, so you have to do that on every screen, every time it paints the screen. So in hyperscreen mode, your sprites will behave like this, and you can put lots of sprites into the vertical border. Many games make extensive use of this, like this game. This is the actual screen area. On the bottom, you have 8 sprites here, just for that status. And the top border, you have also more sprites. All in all, you have 21 sprites on this screen, so how is this possible? This is also pretty easy. You have several compartments of the whole screen and several raster interrupts, and you just reprogram your sprite registers for every screen several times. So in each of those compartments, you can have 8 sprites. This is called sprite multiplexing, and if you're really good at sprite multiplexing, you can either have a good sprite multiplexing routine which can position them anywhere on the screen and position as many as you like, or you can do something like this, which just reprograms the sprites whenever they are painted. And this way you get very big sprites. In this example, this flicker is caused, I think, by the emulator. I think the original game did not have that flicker. Speaking about perfect timing, the timing of the VIC is pretty complicated, and I have to know about the timing to understand some of the tricks. So the VIC and the C6502 share the same amount of RAM, and RAM runs at twice the speed, so they can share it pretty nicely, because on every rising edge, VIC can access RAM, and on every falling edge, the 6502 can access RAM. Because the VIC needs to do lots of memory accesses for the screen, like this. It has 1 memory access per cycle, which is 1 memory access per character, to read the character screen data. So it does 40 fetches per line. But on every first line of every character line, it has to do extra fetches because it has to fetch the indexes from screen RAM. So there it has to do two fetches per cycle. This is possible with RAM, but in this case, the 6502 cannot access RAM anymore, so the 6502 is stalled in that time. If you look at the complete picture, so in all those lines, in all those areas, the 6502 is turned off and cannot do any processing because the VIC is using the bus. These lines are called bad lines, and the rule for the bad line is pretty easy. If the lowest 4 bits of the lowest 3 bits, actually, that's a mistake, of the raster register are the same as the lowest 3 bits of the Y scroll register, then it means this is a bad line. So normally you would have the bad lines there, the red X's, but if I have a raster interrupt at the red dot, and then always make sure that this trigger never hits, and always change Y-scroll so that it doesn't cause the next bad line, it's possible to move down and up the rest of the screen, and it will just paint nothing there. So I can move the whole screen without copying a single byte of data. If we look at this picture that I showed you before, it uses many, many different tricks that I'm going to talk you through now. It's also mostly based on the idea of bad lines. First, let's look at this. There's obviously more than 16 colors involved here. The trick used here is interlacing. You have 50 frames a second on a PAL C64. And if you switch back and forth between two different colors, you might not be able to see the difference, especially if the colors are pretty close to each other. So you could get a purple here, which is different from the built-in purple, so you get an extra color. In theory, this would be 256 colors if you combine those. But of course, if you alternate black and white repeatedly, it will just flicker, and you don't want that. So maybe you get another 10 or 20 colors out of that. So this is the combined picture, and picture 1 would be this, and this is picture 2. On the complete picture, this is picture 1, this is picture 2, this is the combined picture. But even if you look at a single picture, if you look at a detail of that, and if you look at the tiles, an 4x8 block here has more than just the 4 possible colors. In this example, you can easily find 6 colors. The trick you can do there is because 2 of the colors come from screen RAM, and you can change the screen RAM pointer whenever you like. But you have to cause another bad line so that it rereads the screen RAM. So you do this, you cause an extra bad line, so pretty much all of the screen is bad lines, and it will refetch all those. And what you have in effect is not those 4 colors, but in every 4 times 2, you can choose 4 colors freely with some restrictions though. This is called FLI, Flexible Line Interpretation. But there's more tricks used in this picture. There's a lot of border area used. So if we look at the complete picture, the bottom border, we know that already, that's hyperscreen. There's lots of X expanded sprites there. You can see that the resolution down there is not as good, but it's hardly noticeable. And there's also sprites on the left and on the right. This is done with the same trick with the horizontal screen size, but you have to be cycle exact this time because it's only one single character that the screen gets shifted left and right. So you have to be perfectly cycle accurate there, and you have to do it in every line. So these are sprites as well. And on the top, you just overlay a few more sprites to get that. Another trick you can do if you cause a bad line in the middle of the screen, it will just start drawing the next line and fetch the next line in the middle of the screen. So this way you can shift the screen, also without copying anything. So normally with soft scroll, you would soft scroll the first 8 pixels and then copy your complete screen, which is great for a text mode screen, but with a graphics screen you don't have the time. This would take 2 or 3 frames just to copy the whole data. So you can just move it without actually moving a byte. This is called VSP, Variable Screen Position. The game I showed you before, Mayhem in Monsterland, uses this. This is running in bitmapped mode. This is a multicolor bitmap, and it just horizontally shifts the screen and copies the new data on the sides. Another trick you can do is you can compress a line. This is called line crunching. If you just cause a bad line to make the next character line draw already without finishing the current line. If you do this 25 times in a row, you can compress the whole screen into 25 lines. So this gives you the opportunity to move anything up and down as much as you want. If you the problem is that you have lots of garbage on the screen. But if you turn on multicolor and extended background color, the VIC will interestingly always output black pixel on top of everything. So this will, you won't see the garbage there. But you can put sprites on that to work around the black bars. If you use that in a game, it will look somewhat like this. This is Fred's back. You have sprites up there, and you have a real bitmap down there with all the colors, and you can move that in all directions. This is called AGSP, Any Given Screen Position. Normally, if you want to do something cycle exact, like in this example, I wanted to change the screen color and then change it back, it flickers a little. It flickers because if an interrupt occurs, it always has to complete the current instruction, which can be an arbitrary number, or which can be a different number of cycles. So there's a trick that I can smoothen this, which is I have a restore interrupt, and then I set a restore interrupt to the next line, and set a different interrupt handler to that line. I acknowledge my current interrupt, clear the interrupts to make interrupts possible again, and then I do a few knobs, and then the interrupt will hit. And because it was a knob that the interrupt hit, so I know a knob is 2 cycles. It was either in the first cycle or the second cycle of the knob, so I'm pretty close already, so it's 0 or 1 difference. But then in my next handler, I do lots of knobs to go to the end of the current raster line. Then I load the raster register, compare it to the line afterwards, and if it's the same, I go to the next instruction. The trick there is that the branch, if it's taken, takes 3 cycles. If it's not taken, it takes 2 cycles. And I just do the load so that it will just do the trick for me and smoothen the last cycle. And so I'm always cycle exact, like in this example. So we've looked at all the chips now. There's the CPU, there's the CIAs, the SID, we've looked at the VIC, we've looked at RAM, ROM, and the PLA. The PLA is the one that does some memory management logic. Normally, you would have this layout. You can turn off ROM, kernel ROM, basic ROM. You can also turn off basic and kernel ROM. There's a possibility to turn off everything. And if you have external ROM in your cartridge port, you can map that into your address space. You can map the other part so that it replaces basic. And you can map both in. There's another interesting mode, which is the Ultimax mode. The Ultimax mode was a gaming console based on the C64 hardware, which was only sold in Japan and is very rare now because it didn't sell well. It only had 4 kilobytes, or it had less than 4 kilobytes of RAM, and if you're in this mode, so it supports Ultimax cartridges, and if you put those in, that it will go into this memory layout. The tape connector is pretty straightforward. It only has a sense motor and read and write pin. Those go to the CPU's registers or into one of the CIAs. The IAC bus is a serial bus which daisy chain drives. It has these connectors. Those 3 are the interesting ones. It has is data, clock, and attention. The bus protocol works like this. It's not important to understand the details here, but the C64 raises the attention line and sends the command, which includes the drive's number, sends listen, unlisten, talk, and untalk to arbitrate the bus. Because the bus is so slow, because there was originally a chip bug in the VIC-20 in the 1541 disk drive, this protocol had to be done in software, and it's so slow that third-party manufacturers did extra extensions that ran a different bus protocol, like the Epix Fastload cartridge or the Final cartridge, which were up to 20 times faster. The 1541 is the major C64 floppy drive. There's a second version of it. It works on 5¼ single-side double-density disks with 35 tracks out of the 40 possible ones. The number of sectors is different per track, and you have 683 blocks, which is about 170 kilobytes. This is what a track looks like. It doesn't use the index hole. It has sync marks, which is all ones, so it cannot use. So it has to encode the rest of the data so that there are no all ones. This is the header of a sector. There's another sync mark, and this is the actual sector data, GCR encoded, and there's the next sync mark. The directory format looks like this. The file system looks like this. There's the block availability map and the disk name, 16 characters, and also on track 18 are all the file names, which are 16 characters, which is pretty modern. This is what the drive mechanism looks like, and this is the electronics. It's a whole dedicated 6502 computer with 2 VIA controllers, with ROM, RAM, and a PLA. The memory map looks like this. It has 4 kilobytes of RAM. It has an I/O area with 2 VIAs. It has ROM. Interesting is the old Commodore drives had 2 CPUs, one for the bus and the file system, the other one for the drive mechanism. On this 1541, it was shared on one CPU. It switched between those two. One wrote job code and the other one wrote back the error codes. There's also a double-sided version. There's a 3.5-inch version, which wasn't as popular because not as compatible. There was even a